by doing vibration spectroscopy. Just as in rotational spectroscopy, we start with an assumption. And what was the assumption in rotational spectroscopy? Rigid rotor. So every problem that you start off, you have to start with an assumption. And it's only later that you say that look, this assumption is not making that good, the action reality is not this, we got to correct for it and so on. But we have to start the problem with this assumption so that we see at a simple thing, understand the simplistic behavior, and then move on to the more complicated, the realistic things. So in a vibration, the simple thing is going to be, the simple thing is a simple harmonic oscillator. For every vibration problem you do, you bring in this simple harmonic oscillator. I'm sure in physics, when you looked at the pendulum problem, it was a simple harmonic oscillator problem that you really looked at. And how did you ensure that you were looking at the simple harmonic oscillator issues in the pendulum? You made an assumption somewhere. Small oscillations. So you said for small oscillations, sin theta equals theta, and therefore the whole thing works out the way it is. And that's a simple harmonic oscillator. Oh, but what happens if you take the pendulum and leave it out here and then let it oscillate that way? It's no longer a simple harmonic oscillator. It will not give you the behavior of a simple harmonic oscillator, and then you say, well, for large oscillations, we have to treat it slightly differently. But you start the whole process by assuming simple harmonic behavior. And what does simple harmonic behavior actually tell you? That the restoring force is going to be proportional to the displacement. But the restoring force is proportional to the displacement provided the displacement is small. The displacement is like this much. Maybe there is no restoring force, it's broken and gone. There is no there is no restoration force at that point in time. So you can't say, well, you told me there was a restoration force and that's why I pulled it so long. There is a restoration force provided the displacement is small. So V equals the restoring force F equals minus K into X. So they give the minus sign because it's opposite to the displacement, provided X is small. So you pull it in, get back, pull it in, get back, pull it more, it's gone. So that's important because when you pull it in more, you are actually introducing effects of, I don't want to use the word, effects that do not belong to simple harmonic oscillator. So the harmonic oscillator business is simply going to be one which is applicable as long as the displacement is pretty small. We saw that in the pendulum and we will see that over and over again. But what's the real definition of a harmonic oscillator problem? So you have studied that, right? It's a projection of uniform circular motion on the diameter of the circle. So if this guy is going in uniform circular motion on a circle, the projection of that on the diameter is what you get. And then they say the projection of uniform circular motion on the diameter of a circle is basically what we call. So there are different ways of looking at it, but at the end of the day, all these will work provided my displacement is small. So when the molecule is taken and the molecule is not quiet, the molecule keeps doing this. So we will again start by looking at a diatomic molecule. Let's say H2. And the other possibility is HCl. And you see why I'm writing two of them. One has zero dipole and the other one has a non-zero dipole. And very quickly we will get to the issue of a zero dipole and a non-zero dipole. The zero dipole and the non-zero dipole were big issues in rotational spectroscopy, right? H2, will you ever get a rotational spectrum out of H2? No, because it's not a zero dipole. It's silent in the microwave spectrum. HCl, yes, because it's got a dipole and it's constantly changing dipole. While it rotates, can actually interact with the electric field of light. But if hydrogen is only rotating, there is no constantly varying electrical component of the molecule, therefore it could care less for the light, but there is no absorption by it. We will see very similar things also in vibrational spectroscopy. So, what's the potential for a simple harmonic oscillator? We start with a force being equal to minus kx, and therefore the potential, which is the signal, is going to be half kx squared. And what is this k? The force constant, which essentially tells me how strong that bond is. If k is very large, then for the same x displacement, I need a lot of force. So it's something like trying to compare rubber and glass. Rubber has got a very small force constant, you just keep pulling it. Glass, well, you can't. It's a very huge force constant. So K essentially tells me the nature of the spring that's holding the two balls in your oscillator. And in the terms of molecular language, that spring actually is the bond. So K is the force constant which tells me how strong the bond is. So I'm basically going to use K to figure out how strong this bond is. So if I do vibration spectroscopy and get information on K, what information am I getting? I'm getting about the strength of the bond. When I did rotational spectroscopy and got moment of inertia, I got bond structural information. Whereas here I'm going to get information on the bond strength. And therefore that's quite important. And it is this bond strength that I got from rotational spectroscopy by looking at B and D. 4B cube over D is actually going to be equal to omega square, and omega square of the vibration frequency, and vibration frequency depended on the force constant. So whatever information I got there is actually this information, and that's exactly what we said then. That if this bond is very strong, centrifugal distortion can't do a thing to it. But if this bond is very weak, the centrifugal distortion will simply cause havoc for the molecule. So that's the reason why we related the B and D to the force constant. But now we're going to be looking at the force constant in a more direct way by simply looking at the vibration and see how I can get the force constant information. Okay, how does the problem take off now? I take this potential, and once I have a potential, what do I do with it? Professor Schrodinger, I go to get an equation, put B equals half kx squared, and solve the Schrodinger equation now, where B equals half kx squared. When B was 0, you didn't get a particle in a box. When B was 0 in polar coordinates, you got your rotational spectra. And now when B equals half kx squared, and I will assume a one-dimensional oscillator. H2 molecule is just moving back and forth along the x-axis. Therefore, it's a one-dimensional oscillator. A polyatomic molecule is not a one-dimensional oscillator. But I'm not getting into the polyatomic stuff now. In fact, we'll get into the polyatomic stuff after the exam. So you can keep a huge sigh of relief that the first exam, we're not looking at polyatomics, we're looking at diatomics, one-dimensional oscillator. That's the reason why I only have X out here. There's no X, Y, and Z. One-dimensional oscillator, potential is B equal to half kx squared. I take this information, this potential, throw it into the Schrodinger equation, and solve it. Not too difficult, but messy. When you solve the Schrodinger equation for this, it will be really messy. And eventually you can. And in fact, when you take the first course in quantum mechanics, over and beyond what you took in 102, you will see how this has to be solved. You use the power series method, and eventually you go ahead and solve it. And when you do that, what do you get? You get an energy equation, just like we got for the rigid rotor, and we get the wave function corresponding to each level. The energy equation turns out to be V plus a half h nu. Pretty simple. Just like you got h squared by 8 pi square I j plus 1 as your energy equation for the rigid rotor, for a simple harmonic oscillator where V equals half kx squared, energy equation is this. And what about your wave function? It turns out to be the family of polynomials which we call as the Hermite polynomials. Let's not even worry looking at them at this point in time. But for those of you who are interested, you can always go back and see what they look like. For the rotational spectroscopy, we got these Legendre polynomials, here you get Hermite polynomials. At the end of the day, as far as this analysis is concerned, what we want is the energy equation. What's the big difference between the energy equation here and the energy equation we got for the rigid rotor? The rigid rotor energy equation was very similar to the particle box energy equation. Both at n square dependence. N square over there and j plus 1, which is a j square dependence. Why do they have the similarity? Both at b equal to 0 as their operating potential. But here the potential is different. Potential is half kh squared. So you don't expect this to behave like a rigid rotor. You don't expect it to behave like your particle box. It's very different. And I get that equation. What's the big difference between this energy equation and that one? Depends on the first power of the quantum number. And the quantum number is this. Or the vibration quantum number V. Nu is the vibration frequency. The frequency at which the molecule vibrates. H, of course, is your very celebrated Planck's constant. So V plus half is the energy equation. So if the energy equation depends on the first power of the quantum number, how will your energy level diagram, that ladder, how will it look like? Equally spaced. Okay? So the first one, because we have to now decide whether we want to keep V equal to 0 or V equal to 1 as our lowest level, because this is something we always have to break our heads on. Particular box, was n equal to 0 allowed? No. N equal to 1 was allowed. Because if I put n equal to 0, I am going to irritate some very celebrated physics professor. So we can't do that. When I put j equal to 0 for the rigid order experiment, perfectly fine. Because I didn't, not by IISER. Here, when I put V equal to half, V equal to 0, what's the energy going to be equal to? So even at the lowest level, if this was V equal to 0, the molecule still has some energy. And as long as it has that energy, the Heisenberg uncertainty principle is therefore not violated. I am perfectly okay with it. And therefore, V equal to 0 is allowed for the oscillator problem. And the energy corresponding to V equal to 0, which is half HU, is what we call as the 0 point energy. So if we ever asked what's the 0 point energy for a simple harmonic oscillator, it's half HU. What does that really mean? It simply means that if I take this molecule and get it down to absolute 0, it's going to sit in that V equal to 0 level, and what is it going to do? It's going to be oscillating because it's an energy pool. So the world isn't quiet even at 0 Kelvin because molecules are still oscillating, and you have this 0 point energy present there. Rotation will cease. We are frozen. Oscillations don't cease. And therefore you will find that when you get the molecule down to V equal to 0, and below which you cannot get them, the molecule still has a residual energy which we call as the 0 point energy. Where does the V equal to 1 come? Up here. And what is the energy difference between V equal to 0 and V equal to 1? HU. It's half HU for V equal to 0, 3 half HU for V equal to 1, and the difference in energy between these two levels will be HU. What happens after that? So unlike the rotation problem in which the energy levels kept pulling away, in the case of a harmonic oscillator problem, the energy levels are actually equally spaced. All these levels are going to be equally spaced. But again, that's true only for a simple harmonic oscillator. Keep nailing that in your mind. Because some couple of days later I'm going to come back and tell you, well, it's only for a simple harmonic oscillator. For a real oscillator, it is not the case. Just like we said for the rigid rotor. We're going to come back and sort of correct ourselves at some point, saying that this equally spaced stuff is only good for a simple harmonic oscillator. But if the oscillator is simple harmonic, this is true. The spacings are equal. Now let me do one thing. Let me draw the potential energy diagram for a simple harmonic oscillator. And what do I mean by saying draw the potential energy diagram? I'm simply going to plot V in that. And what should V look like? Half k squared. Now it is this potential which I can really, let's try to understand what the potential is trying to tell me. What is this potential really trying to tell me? It's trying to tell me how the molecule will oscillate. It's actually trying to tell me how the molecule is going to oscillate. What is this point over here going to be? It's called the equilibrium internuclear distance. And this is what we were trying to, in the rotational problem, when I said I equal to mu r square, and we found out what r was, we were pretending as if we were getting this Re. Very soon we will see what that Re really means. It was this equilibrium internuclear distance, which is this distance, that is characteristic of a molecule. What is this potential energy diagram telling me? It's a potential energy diagram for a diatomic molecule. Okay, there are two atoms. So I'm going to fix one atom on this axis and not let it move. It's the other atom that is going to be going back and forth, and therefore I am mimicking this oscillation business by keeping one atom fixed and moving the other. Of course, otherwise I kept showing you like this. it's only the relative motion that's important. So I'll keep one guy fixed and keep moving the other, and that's still a valid picture. So I'll keep this fixed, and let me say that this is the energy of this oscillator. What is this oscillator going to do? It's going to move up till here. Can it go beyond this? No. This potential is simply telling me this is all you can go up to. You can't go beyond this. Okay, then what do? I retreat. I come back. And can I keep going forever? No. This end is actually going to tell me you can't get any closer than this. So, when this guy is fixed, the other atom can at best go up till here, or it can go up till here, and therefore the two limits are actually decided by this parabola or this potential. Supposing I gave more energy to the oscillator and I made it sit here, what is going to happen now? It can go a little bit more on this side, it can go a little bit more on this side, essentially meaning that the more the energy of the oscillator, it can do this. The less the energy of the oscillator, it can just do this. So how much it can go out and in will actually be decided by the energy of the oscillator, and who else? The potential. So the potential actually decides for me as to how that's going to be. If k is very small, how do you think the parabola will look like? If k is very small, what will the parabola look like? It's going to open up, right? It's going to be a flared out parabola. And therefore, if k is small, it will still be a parabola, but something like this. What is this flared out parabola actually telling me? What is it telling me? It's simply telling me that now this guy can go longer distances there, come back. In other words, a small value of k actually tells me the force constant is small. If the force constant is small, what can the atoms in the molecule do? They can go to longer distances and come back. They are not really being held back. And therefore, a smaller force constant actually tells me that I can move much to greater distances. A very strong force constant, what does that tell me? Follows. So the stronger the force constant, larger the value of k, what is the potential going to look like? Like this. And smaller the value of k, what is the potential going to look like? This. And you got to keep this in mind. Because every time you see a potential curve that looks played out, what is it that you will immediately tell yourself? That's a weak molecule. And if you see a potential that is sort of closing in, like that one, immediately you know for yourself that I'm looking at a molecule whose force constant is quite large. Therefore, it's a pretty strong bond I'm looking at. So, just by looking at the potential energy diagram, which depends on k, I actually start getting information on how strong or weak that molecule, that bond in that molecule is going to be. Okay. Now let's see. Now what I am doing is, I have the potential and V equal to 0. What is the energy of V equal to 0 going to be? Half h nu. So I want the energy, it is half h nu. I locate a horizontal slope in that potential. And what is this going to be? V equal to 0. Where will V equal to 1 be? It will be up there at a distance h nu away from this line. And where will V equal to 2 be? Up there. This is h nu, this is h nu, this is half h nu, and so on. So I can actually draw the energy level diagram within that potential, and we will see what information we can get. Go back to your pendulum problem. When the pendulum is oscillating, what is constant in that? What is conserved? Total energy. What happens at the extreme position? All the energy is potential. Some potential, some kinetic. Here, all kinetic, and again this goes on. So as the oscillator is going back and forth, you are actually converting potential to kinetic and kinetic to potential and back and forth, and that's the same thing that should happen over here. But how do you recognize that? And how do you estimate the amount of energy that is going back and forth? And that's the same way. At the extreme end, what should be the energy? This is the total energy. At the extreme end, how much of it is potential and how much of it is kinetic? All of it is potential. At this extreme end, all of it is potential. Let me come in over here. I know that some of it is potential and some of it is kinetic. But what's the total energy? It's still this much. That's the total energy. So that is conserved right through. There's no problem with that. But when I get here, what happens now? This part has to be potential because there's a potential energy diagram. So this part of it must be the potential energy part. And what is the kinetic energy part? It must be this. Go to the middle. So what can you generalize this as? That part of the straight line, which is above the potential energy curve, must be the kinetic energy part of the energy. And the one that's below the potential energy curve must be the potential energy part. When I come right to the middle, what's happening? Everything is above the curve, and therefore all of the energy must be kinetic. There is no potential energy part. But again, as it moves past here, that part of it is kinetic, this part of it is potential, and when I get to this point over here, so all this, so as the oscillator goes back and forth, all the energy that is described below the potential is going to be the potential energy part, and all the energy out here is going to be the kinetic energy part, and therefore you will find that during the entire oscillation, you are actually transforming kinetic to potential and potential to kinetic, but how much of it is being conserved can be very easily looked at this diagram, and you will get that information. Of course, it applies to every level. Now, how much is this energy roughly? What are the spacing in rotational spectroscopy? Few wave numbers, right? 2 wave numbers, 3 wave numbers, 5, 10, and that's it. Let's get an order of magnitude estimate for vibration. How much is the energy you think I need to go from one vibration level to the next vibration level? When I go to the next vibration level, what is different with me? I can just go longer distances. That's basically what it is. I have more energy and I can go to longer distances. How much energy do I need to jump from V0 to V1? Typically, you have done the experiment, and where are all your features coming? 1000 wave numbers, 2000 wave numbers, 3000 wave numbers, right? Your x-axis in your FTIR spectra that you recorded are all in the realm of 700, 1000, 2000, 4000. So I'm essentially looking at energies of the order of a few thousand wave numbers to be able to go from one level to another. So when the molecule absorbs that energy in your FTIR experiment, it is actually absorbing energy and jumping from V0 to V1. Of course, after a little while it will come back because it can't stay there forever. But I am actually using energy in the realm of a few thousand wave numbers as opposed to a few wave numbers for rotational spectroscopy. Let's assume this is 1000 wave numbers. If the gap is 1000 wave numbers between V0 and V1, what should be the relative population in V1 at room temperature? What is KT at room temperature? 200 wave numbers. So 1000 by 200, how much is it? 5. I don't know what was so wrong in what I said. So 1000 by 200, how much is it? 5. So it's e power minus 5. That should be the population. No degeneracy issues over here because degeneracy is 1, 1, 1 everywhere. There is no 2j plus 1 degeneracy or anything of that sort. Well, there are some degeneracy, we'll come to that later. For a diatomic, there is no degeneracy issue. For a diatomic, there are no degeneracy issues as far as the vibration levels are concerned. You don't have to worry about that degeneracy factor in front of your exponential. So e power minus 5. And how much is e power minus 5? How much is e power minus 1? 35%. E power minus 2? 15%. E power minus 3? 5%. E power minus 4? 2%. E power minus 5? 1%. So how much of the population in these levels? About 99% is sitting here and about 1% is sitting there. If you go to 2000 wave numbers, 3000 wave numbers, some of the peaks that we saw were at 2000 and 3000. What happens? Well, there's hardly any population. In other words, when you're looking at vibrational spectroscopy, almost every bit of your population is sitting in V equal to 0. In rotational spectroscopy, it was not that. We even were talking about a most probable J, which was like J10 or J12 or whatever. The population was actually sitting in higher J levels. In vibrational spectroscopy, the population is concentrated in V equal to 0. Of course, if you're looking at vibrations of molecules which have like 200 wave numbers, 300 wave numbers and so on, very low frequency vibrations, there you will see molecules sitting in low energy states. But otherwise, for all these 1000, 2000, 3000, 4000 frequency vibrations, you will see that the population is essentially dominated by V equal to 0. So now what's the next thing I need to do? I know the population. I know where the population is. The population is all sitting here. And now if I shine light, what do you think it will have? It will do. If the frequency of light is appropriate, it matches this spacing, what will the molecule do? Take the same energy and jump up here. And therefore I make a V equal to 0 to V equal to 1 transition. First condition, the molecule must have a light with the appropriate frequency. But what's the next condition? Selection rules. What are the selection rules for a rotor? Delta J equals plus minus 1. What is the selection rule for oscillator? You have to do it the same way. Take an integral, put your wave functions and solve and see what quantum numbers can be connected. And it turns out, for a simple harmonic oscillator, delta V has to be plus minus 1. This can be proved if you take the wave function, the harmonic polynomials of these different levels and solve the integral for the transition probability integral, you can actually show that the delta V equal to plus minus 1 selection rule will have to be obeyed. First, frequency has to be appropriate. Second, selection rule has to be right. Which essentially means I can go from 0 to 1, but I can't go from 0 to 2. And what are 0 to 2 called? They are the higher order frequencies. I don't know how many of you are interested or good at music. There's always the overtone vibration, right? You pluck something, you have the fundamental and you have the overtone vibration. It's at twice the frequency. This transition would be at twice the frequency if it ever were to occur. And therefore we call them as overtone transitions. But in a simple harmonic oscillator, unfortunately, you don't have overtone transitions. You only have fundamental transitions. 0 to 1, allowed. 1 to 2, allowed. So if you want to go from 0 to 2, you have to do it in 2 steps. Take the molecule up here, and before it's got a chance to come down, take it up there. Not so easy. In other words, we are stuck with fundamental transition 0 to 1. If I had molecules with V equal to 1, let us say the frequency was quite small, let's say 500, and there is some population out there, then what will happen? 0 to 1 can happen, 1 to 2 can also happen. But will you ever be able to find out that 1 to 2 really happened? Even if 1 to 2 were to happen, can you ever find that out? What's the problem? Same frequency. H2, H2. So at H2 you will get one peak, and how do you know that one peak, this much of it was because of 0 to 1 and this much was because of 1 to 2? That's very, very hard to say. Therefore, things might have happened, but you don't know. So that's another problem. Even if the band from 1 to 2 were to occur, you would not be able to see. So you will just see one line, which is 0 to 1 transition, but who knows, 1 to 2, 2 to 3, 3 to 4 might all have been occurring, but there's no way for you to figure out that those things were actually occurring. Simply because the frequency all happens to be the same. In other words, all the transitions, 0 to 1, 1 to 2, 2 to 3, are all singing for you at the same frequency. And you can't tell who is really singing. They're all doing it at the same frequency. That's the problem. Before I leave, I have to tell you this, because you don't go home thinking that my frequency is right and my delta V equal to plus minus 1 selection rule is right, everything is fine. There's a very important rule on the third one, and that is dipole moment